If you look at Mercury through a telescope, it is incredibly easy to assume you are just looking at our moon. At first glance, it appears to be a gray, heavily cratered, dead rock floating in the void. But step onto that surface and the illusion shatters. Because Mercury lacks an atmosphere to insulate it and trap heat, the side facing the sun bakes at 800 degrees Fahrenheit, hot enough to melt lead. Meanwhile, the dark side instantly radiates its heat away into space, plummeting to a bitter -300 degrees. The orbital mechanics at play here are equally alien. Mercury rotates exactly 3 times for every 2 trips it makes around the sun. If you stood on the surface, a single day from sunrise to sunrise would take 2 entire Mercurian years. You would watch the sun rise, hit a point in the sky where it seemingly stops, moves backward, and then resumes its path forward. This is a world defined by its extremes. It is the most heavily battered, wildly fluctuating environment in the inner solar system. Yet, despite being relatively close to Earth, it took decades longer to properly study Mercury than planets much further away. Sending a probe to the inner solar system is an absolute nightmare of orbital physics. The issue is the sun. As a spacecraft travels inward, the sun's massive gravitational pull acts like a whitewater rapid, violently accelerating the probe. By the time it reaches Mercury, it is moving entirely too fast to be safely captured by the tiny planet's weak gravity, shooting past it into deep space. To solve this, NASA engineers mapped a 7.9 billion kilometer detour for the MESSENGER probe. Instead of flying straight there, the spacecraft spent over 6 years looping the inner solar system, skimming past Earth and Venus multiple times to systematically bleed off its momentum using atmospheric drag and gravity. When MESSENGER finally slowed down enough to enter orbit in 2011, the data it sent back broke nearly every existing model we had for how planets form. We had to weaponize the gravity of 3 different planets against the solar system's deepest gravity well just to park a camera next to this tiny world. Looking deep inside, MESSENGER revealed a bizarre anatomical anomaly. A standard rocky planet like Earth has a small iron core surrounded by a thick, heavy mantle. Mercury is almost the exact opposite. It is mostly core, wrapped in a razor-thin layer of crust. For years, astronomers assumed a massive head-on collision early in the solar system's history simply blasted the rest of Mercury's rock away. But MESSENGER found highly volatile elements like potassium and sulfur sitting right on the surface. A direct head-on impact would have generated so much heat that these chemicals would have instantly vaporized. Instead, the data points to a hit-and-run collision. A larger protoplanet struck early Mercury at a shallow, glancing angle. It sheared off thousands of miles of outer rock, stealing the planet's mantle while leaving its heavy core intact and relatively cool. This violent scrape also exposed a deep, ancient ocean of magma. As that magma eventually cooled, lighter carbon minerals like graphite floated to the top. That is why Mercury is visibly darker than the other rocky planets. It is completely coated in pencil lead. What we are looking at today is the surviving iron heart of a much larger world, bearing the permanent scar of a cosmic theft. And yet, Mercury hides an even stranger contradiction. Sitting directly next to the sun, on a surface that can melt metal, is an estimated 1 trillion tons of water ice. The first hints of this came from Earth. In the 1990s, the Arecibo radio telescope bounced radar signals off Mercury and detected highly reflective patches near the poles. MESSENGER spectrometers later confirmed those bright spots were frozen water. Earth's axis is tilted, which gives us seasons and ensures sunlight eventually touches almost everywhere. Mercury stands almost perfectly straight up. Because of this 0-degree tilt, the sun always sits extremely low on the horizon at the poles. Its light rays skip right over the rims of deep craters, leaving the crater floors in permanent, freezing shadow. Astronomers call these cold traps. Over billions of years, ancient comets, which are essentially giant dirty snowballs, slammed into Mercury. The water that landed inside these permanently shadowed craters instantly froze and remained safely locked away. By sitting perfectly upright, Mercury manufactured a permanent sanctuary for ice, just millions of miles from a burning star. As if holding ice near the sun was not strange enough, Mercury's surface is heavily scarred by massive fault lines. These steep cliffs, known as scarps, stretch for hundreds of miles across the terrain. They are the physical result of thermodynamics. Because Mercury is mostly an iron core, it is steadily losing its internal heat. As that giant metal center cools, it physically contracts. With the core shrinking inward, the solid rocky crust on the outside has nowhere to go, so it buckles, cracks, and thrusts over itself like a drying grape. For a long time, scientists assumed this violent contraction was ancient history, that the planet had completely frozen solid billions of years ago. But MESSENGER scanned the surface and found extremely small, pristine fault scarps cutting through the landscape. If these were old, they would be covered in impact craters from billions of years of asteroid strikes. The fact that they are smooth means they formed recently. Mercury is still tectonically active. It is actively crushing its own surface in real time as it cools. Stripped of its outer layers in a prehistoric collision, baked by extreme solar radiation, and constantly fracturing its own crust, this tiny planet has absorbed every punishment the solar system could deliver. But it might not be the victim forever. Out in the gas giant region, Jupiter's massive gravity exerts a slight continuous tug on Mercury. Because Mercury's mass is so small, Jupiter rhythmically pulls on it, slowly stretching its orbit from a tight circle into an elongated ellipse over deep time. Computer models project two distinct endings for this world. In one scenario, the Sun eventually exhausts its hydrogen, bloats into a red giant, and swallows Mercury whole. In the other, Jupiter's gravitational tug stretches Mercury's orbit until it breaks free of its current path, sending it careening through the inner solar system. Depending on how orbital mechanics play out over the next few billion years, the smallest, most battered rock in the solar system might quietly wait for the Sun to consume it, or it might become the apocalyptic end for one of its neighbors.